Hello, I'm Kübra Keskin. I'm going to present my term project. The title is Balanced Steady-State Precession, in short Balanced SSFP. Balanced SSFP is type of gradient echo MR sequence. It is called steady state since after some TR intervals, magnetization vector reaches the steady state value. It is called balanced since all of the gradients are compensated by adding refocusing gradients. Therefore, integrals of them should be zero, as we can see from the image. It's a fast imaging sequence. Since TR is very short, it should be much less than T1 and T2. And due to symmetry, echo time is half of the repetition time. And also, it provides high SNR. If we want to derive the signal equation, we should find the steady-state magnetization. Basically, the principle is that at the beginning of each TR interval, magnetization vectors should be same. If we apply what happens in one TR interval to the magnetization vector and equate it to the same magnetization at the beginning, we can get the steady-state value. Transverse magnetization just after RF pulse is then formulated as in the slide. Then we can get the magnetization at echo time by adding the effect of T2 decay and of resonance frequency. If we look at the signal evolution over changing of resonance frequency, we can see that signal magnitude is highly dependent on the of resonance frequency. We can observe that for some frequencies, signal intensity drops. If we change the flip angle, signal magnitude again changes as seen in the figure. Also, different tissues produce different magnitudes due to T1 and T2 values. If we look at an example image, we can observe the signal losses caused by off-resonance frequency. They are called banding artifacts. Position of these artifacts can be changed with shimming, changing the TR value or changing the phase of the RF pulse. In these images, phase of the RF pulse is changed. To eliminate the banding artifact, people offer phase cycle balanced SSFP, which means that at each TR, phase of the RF pulse is incremented with a constant value. I will demonstrate what is changing by phase cycling with a simple example. We look at the signal profile over the phase offsets of a voxel. If we apply pi/2 phase increments, we will get shifted profile. Same happens with pi and 3 pi/2 phase cycle signals. Amount of shift depends on the phase increments, as you can see. In this manner, we can get different intensity levels for a voxel. Therefore, this information can be utilized to remove banding artifacts. To demonstrate the phase cycle PSSFP, I prepared a simulation application in MATLAB. This is the user interface of the application. Two upper figures demonstrate the magnetization vector in three-dimensional space and transverse plane. Two bottom figures provide magnitudes of the longitudinal and transverse magnetization of upper configuration. Here, blue dots are acquisitions we can get with different phase increments. And it is interesting that they follow an elliptical path. In this app, user can also simulate different tissues. Also, user can change the TR, flip angle, and off-resonance frequency, and the number of phase cycles. Here is a short demo of the application. We can see what happens when we change off-resonance frequency. Here. Also, we can see how flip angle changes the magnetization vectors in 3D and 2D. You can also play with the TR value. And that's all. Thank you.